Hello and welcome back to AGT STEM. Today we're going to be watching a video about Neptunium. So, without further ado, let's hop to it. All I know is that it sounds like Neptune, so maybe it is on Neptune. It probably didn't come from Neptune, but maybe it's on Neptune. Or maybe they just chose a random name. I don't know. I've got no clue. So, we need to watch it.
I've never seen any of these elements before, and so it's really good because I now feel that I know them a little bit better. I mean, you never really know a chemical till you've tried doing reactions yourself. So it's like meeting somebody very quickly at a party rather than having dinner with them, but still it is a start. I know more about chemistry than I did at breakfast this morning.
Okay, we're here in the central laboratory and I'm going to show you some Neptunium samples. This is Neptunium in solution. It's been dissolved and it's in nitric acid at the moment. And what we've got here are three different oxidation states of Neptunium.
Well, down at the bottom of the periodic table things are very different. There's all sorts of phenomena which are really very unusual, just to do with the sheer size of these elements, how the electrons behave.
When I hear of nuclear fuel and nuclear power plants and things like that, I've heard of uranium and I've heard of plutonium, but you don't hear people talk about Neptunium. What's Neptunium got to do with the nuclear process at all? Where does that even come from?
Okay, so Neptunium is one of the byproducts of irradiating nuclear fuel. It's one of the actinides that's produced.
So when you use the uranium or plutonium to make a nuclear reactor, you could get Neptunium. I wonder if you could use the Neptunium to make the reactor. Maybe can, maybe can't, I don't know. Pretty much everything is radioactive once you get down to the bottom of the periodic table. Dangerous, toxic, radioactive everywhere.
And we need to control it within the PureX process to make sure it goes to the right place, it goes to the correct waste stream.
It has to be separated from the other elements when you're purifying the waste from nuclear reactors, and it has a minor use in that you can use it to make the isotope of plutonium, plutonium-238, which is used in batteries, but that's plutonium and not Neptunium.
So of all the elements in the periodic table, I understand it has the largest liquid range, by which I mean from going from a liquid phase to a gas phase, you have to put in an extra 3,363 degrees C. Strictly speaking, it's Kelvin, but a degree C is essentially the same as Kelvin.
When we dissolve the irradiated fuel, the Neptunium goes into solution and it can exist as Neptunium-4, Neptunium-5 or Neptunium-6.
Like many other metals, Neptunium has a number of these so-called oxidation states. In this case, Neptunium-4, Neptunium-5 and Neptunium-6. And what these are:
Neptunium-5, Neptunium-4 and 5 and 6, they kind of remind me of like copper, like if you see a penny, especially I think it's 5, the one that was kind of light blue looking, very similar to like the color of a penny or copper when it oxidates.
Are atoms of Neptunium which differ with the number of electrons they've lost. So they can switch. So Neptunium-5 can lose an electron and go to Neptunium-6, or it can gain an electron to go to Neptunium-4. In fact, Neptunium-5 in solution is not very stable, and if you get the nitric acid concentration not correct, half of it goes to Neptunium-6 and half of it goes to Neptunium-4. Much of the skill in this area of chemistry is manipulating the strength of the nitric acid to get the right oxidation you want at the right time. And they have bottles over here of different strengths of nitric acid which they can drip into the solution at the right time.
So when we're doing research on advanced reprocessing, we'd like to send the Neptunium all in one direction, which means controlling these oxidation states. We're working on a flow sheet actually to convert all of the Neptunium to Neptunium-6 and keep it there. There's a chemical reagent within nitric acid that is produced through radiation chemistry called nitrous acid, and having that in the correct amount also helps stabilize the Neptunium-5 into Neptunium-6.
It's not even a dramatic chemical reaction, it's just tweaking a concentration.
There are a lot of competing chemical reactions going on. They all change at different rates with temperature. So it's finding the balance where you can drive the equilibrium towards Neptunium-6.
So Neptunium comes straight after uranium in the periodic table, and it's just before plutonium. And it's not a coincidence that it's called Neptunium, because if uranium, of course, is named after Uranus. Plutonium is named after Pluto, and if you think about the order of the planets, although Pluto now isn't a planet, I understand, Neptune is right there in the middle.
People don't use the name Neptunium very often because they don't talk about the chemistry of that element very often either.
Actually, there's another thing about Neptunium, which is that it almost could not have been Neptunium because germanium was nearly called Neptunium. Of course, you can only have an element name once, so if germanium had been Neptunium, then Neptunium would be something else.
All right, you ready? I'm going to ask you a question you weren't expecting. What do you know about the planet Neptune?
I know it's a long way from Earth.
Do you know what it looks like? I love my planets. Do you know which one it is?
Yeah, I always think it's the one with a green tinge to it, but I'm not sure if that's right. Because they become a bit bluer, or yeah. Cause I always think of Pluto as being blue. You see.
No, Pluto is like rocky, but Uranus is kind of greeny. Although even that's not that greeny. Neptune's the bluey one.
Okay.
Yeah.
Well, that was fun. That was nice. And Uranus is the one that is a little more green and a lighter blue. And Neptunium is the dark blue. And Pluto's not blue at all. Thank you so much for watching, and we'll see you next time. Stay smart. Bye-bye.